Okay, the recording has kicked in, so I guess it's time to start. What we're starting on is the second last of our respiratory content lectures. You might recall next week we've got the last of our 2 clicker sessions, which is happening next Tuesday, this time next week. Next Monday we're looking at clinical applications. The reason I'm doing that last and doing the regulation now is that obviously your workshops this week will rely on this knowledge. So I obviously had to do it today rather than next week. So, as I said, what we're doing today is to look at the regulation of the process of ventilation and respiration, that is breathing and gas exchange. Now, that obviously is pivotal to how any body system works and is the sort of underpins the study of physiology. You know, how do we regulate the body systems? The answer to that is fairly straightforward, but as always, there are different levels of complexity depending on how deep you want to dig. So the basic summary statements I have for this lecture are, as always, very simplistic. It reminds you, or tells you, if it's the first time you've looked at this system, it tells you that the basic rhythm of breathing is controlled by respiratory centres located in the part of the brain called the brainstem. Which is hardly surprising. The brainstem contains many of the rudimentary, fundamental things that allow us to survive. Okay, we'll talk about that as we go through the lectures. But that's the basic rhythm. And what you know, should know, that we can modify that basic rhythm, both consciously and unconsciously. And the modification of how we breathe is in response to inputs primarily from sensory receptors in other parts of the body, particularly the brain itself. Now, before we go into it, what we can establish from what we've learnt yesterday, it was yesterday, what we learnt yesterday is that, what are we trying to regulate? Often with physiological systems, we're trying to we modify things in order to achieve a set point, or set points, plural. Now, in respiration, what are the set points we're trying to maintain? Well, yesterday we learnt that they are an appropriate pH in the body, particularly the fluid surrounding the brain. We'll talk about this as we go through. And the appropriate pH, a fairly neutral pH that we're trying to regulate, is influenced by the partial pressure of carbon dioxide. Remember yesterday we learnt that carbon dioxide binds with water to form carbonic acid, which dissociates into hydrogen ions, which can change your pH, and bicarb. So our pH generally changes as a consequence to changes in partial pressure of CO2. So we're trying to maintain appropriate levels of partial pressure of CO2, thereby keeping a nice neutral pH of the fluid, particularly surrounding the brain. Obviously to protect the nerves, to optimise functionality and survival. The other thing we're trying to regulate, and by the way, what was the partial pressure of CO2 that we're trying to regulate? A PCO2 of about 40. And with oxygen, don't forget oxygen, even though, as I said, it's not as important as CO2. But in some instances, we do try and preferentially regulate our partial pressure of oxygen to maintain appropriate oxygen delivery to our tissues. And what was the PO2 we're trying to regulate? A PO2 of 100. So they're the set points we're trying to achieve. Have that in the back or forefront of your mind as we go through these lectures. So let's look at the basic control of breathing. What makes us breathe? Well, the simple answer to the question, what makes us breathe, is, in fact, as we said, the brainstem and the respiratory centres located in the medulla and pons of the brainstem. So there are three parts of the brainstem. For those of you who've done anatomy this year or last year, or both, you've got the midbrain, the pons and the medulla. The pons and the medulla contains nerve cells, which we call the respiratory centres, and this sets the basic pattern of our breathing. So you and I breathe because of these nerve cells in the respiratory centres in this part of the brain. Okay. What they do is have neural connections with the key muscles of breathing. And you already know that the key muscles of breathing are the diaphragm and the external intercostals. So the connection between the respiratory centres and those muscles is via the phrenic nerve to the diaphragm and the intercostal nerves to the external intercostals. Straightforward. The basic pattern of neural activity going to those muscles is indicated fairly basically in my diagram at the bottom of this overhead, such that each of those pink stripes represents an action potential, in case that wasn't obvious. So what happens is that these respiratory centres initiate action potentials that travel along these nerves to the muscles in this sort of pattern. So we get a volley, we call this a volley, which is more than one, a volley of action potentials going to the muscles, the diaphragm and intercostals. And obviously if you send an action potential to a skeletal muscle, it will contract. And then the respiratory centres become quiescent, which is just a fancy word for doing nothing. And you already know from last year or last semester that if you don't send action potentials to skeletal muscles, they relax. And we already learnt that that means you will exhale. And this is the basic pattern of activity. Now, if that basic pattern of activity does not meet your set points of pH, partial pressure of carbon dioxide and partial pressure of oxygen, you need to modify that pattern. So what options do we have? So before we look at this pattern of activity, if you want to get rid of more carbon dioxide because your pH is not right, or if you want to get more oxygen to your tissues because you haven't enough, what two things do we do? Just in basic sort of thinking. What do you do when you need to get rid of more CO2 or get more oxygen into the body? You breathe faster or more rapidly. What's the second thing you do? You breathe more deeply. Well done. So let's look at this basic pattern of activity and how might you do each of those things? Well, certainly we'll start with breathe more deeply. What do you need to do to this basic pattern? How do you modify this basic pattern in order to make you breathe more deeply? Yeah, well done. Send more action potentials to the muscles. They will contract harder. And we learnt last week that that means you'll take a bigger breath in. So more action potentials will increase the depth of your breathing. The other thing, breathing more faster, more rapidly. How can we achieve that? Obviously, we've got to reduce the duration of the quiescent period where nothing's happening. So in effect, these inspiratory volleys become closer together. I mean, that's a limitation to how fast you can breathe. Obviously, you can't breathe 200 breaths per minute because you need to have time to get air in and to get air out. So there is a limitation. But you just reduce this quiescence period. The inspiratory volleys become closer together, and that means you breathe more rapidly. And that's all we're doing. It's nothing more complicated than that. Now, just to always add a challenge, if I said to you, you've got both of those options, and I'm not saying we don't do both of those things, that is breathe more rapidly and more deeply, but what is the most efficient way of increasing your PO2 or blowing off more carbon dioxide? So you can breathe more deeply or more rapidly. Which is the most energy efficient way of achieving our goal? Breathing more deeply, right, because it does take work. You're contracting muscles harder, but every mil of air that you take in addition to that which is normally taken in, is fresh air from the atmosphere. Breathing more rapidly certainly will increase your PO2 and get rid of CO2, but it isn't the most energy efficient way because remember, 150 mils of every extra breath is not going to the alveoli. It's not contributing to alveolar ventilation. So that's why you and I, and you've probably never thought of it, but when you do try and increase your breathing, you tend to breathe more deeply, more so than more rapidly, because it's much more energy efficient. Okay, some good things out of that discussion. Now, that's how we do it, but why do we do it, or when do we do it? Now, I said earlier, it all comes down to these chemical signals, or basically in response to changes to certain things in the body. And what are those things? Well, I obviously flagged what they were. We have chemoreceptors in our body, and I'll talk about them in a minute. As the name suggests, they are receptive to chemicals. What chemicals? Well, 3. Not to the same degree, we'll talk about that in a minute. But certainly we are constantly monitoring our PCO2, or partial pressure or concentration of carbon dioxide, the PO2, partial pressure of oxygen, concentration of oxygen, and the pH, which, as we learnt yesterday, is directly related to the PCO2. We'll reinforce that in the next slide. So one or more of those changing, and I've got arterial, that means it's what's happening in the arteries, not so much the veins. It's what's in the arteries that's important because that's delivering material to the body. Changes to any of those will be detected by the chemoreceptors, and that's a plural word because we have more than one in the body. We in fact have 2 sets of chemoreceptors, peripheral and central. Now, any time we talk in anatomy or physiology about central, what are we referring to? The brain. When we talk centrally and anatomically and physiologically, we generally mean the brain. So we'll talk about the central chemoreceptors, which are located in the brain, and the peripheral ones, which are located outside the brain. We'll say where in a minute. Those chemoreceptors have connections with the respiratory centres. Now, what sort of connections can you imagine these chemoreceptors have to the respiratory centres? If you want to connect 2 bits of the body really quickly, how do we do it? Nerves. Well done. So we have sensory nerves connecting the chemoreceptors to the respiratory centres, which I spoke about in the last slide. And those respiratory centres, as we know, influence via nerves, motor nerves, to the skeletal muscles, making us breathe. Let's look at those chemoreceptors in more detail. By far the most important chemoreceptors you and I have in our body are the central ones. So, remember, the central chemoreceptors are not making you breathe. The respiratory centres make you breathe. The central chemoreceptors modify your breathing when required, when you're not achieving your set point. Those central chemoreceptors are located, as I already flagged, in the brain, particularly the medulla of the brain. Now you might say, yeah, that's right next door to the respiratory centres. Well, yeah, good. They need to be next door, so it's very quick, rapid communication. They're only a few millimetres away. The central chemoreceptors monitor the pH, which, as we learnt, yesterday, and as we'll reinforce in a minute, is totally related to, nearly in all circumstances, are totally related to the partial pressure of CO2 in the brain. And by in the brain, we're talking about the fluid that surrounds the brain. Anyone remember what that's called? What do we call the fluid surrounding the brain and spinal cord? In this instance, the cerebral spinal fluid, or CSF. Well done. So the central chemoreceptors are monitoring the pH of the CSF, which is influenced by carbon dioxide in the CSF. So if the central chemoreceptors are the most important chemoreceptors we have in the body, and if they are associated with pH and CO2, we now know that CO2, carbon dioxide, is the most important factor controlling the rate and depth of our breathing. And we'll see why in a minute. It all comes down to this key equation. If you don't know this off by heart already, you must know this off by heart. It's not particularly complicated. It's central to control of our breathing. And we learnt about it yesterday. We are now emphasising it really importantly today. Carbon dioxide in the presence of water will form carbonic acid. Now, that will happen very rapidly if there's the enzyme carbonic anhydrase that we spoke about yesterday, which is in red blood cells. But even in the absence of the enzyme, it will happen, but just much more slowly. Now, there's a little bit of that enzyme in CSF, cerebrospinal fluid. So, whether it's in red blood cells or cerebrospinal fluid, H2CO3 or carbonic acid is still very unstable. Doesn't matter where it is, it's unstable. And it will dissociate into hydrogen ions and bicarb. Bicarb does not contribute to pH, hydrogen ions do. And this is always, as the arrows suggest, this is always in equilibrium. By that I mean that if you increase the partial pressure of carbon dioxide, the concentration of carbon dioxide, as I said earlier, we tend to use the word partial pressure when we're talking about gases in solution. It's the same as concentration, if you like. So if we increase the partial pressure of CO2, maybe because you're exercising, maybe because you're not breathing sufficiently, whatever the reason is, if you increase the partial pressure of CO2, because this equation is always in equilibrium, that will drive the equation to the right, and hence you'll increase both hydrogen ions and bicarb in order to maintain equilibrium or balance. Increased hydrogen ions will make the pH go up or down? Down, more acidic. So increasing the hydrogen ions makes it more acidic. This is very dangerous to nerve cells. You don't want the pH to go high or low. It will kill you very quickly. So we need to respond to this change in hydrogen ions in the cerebrospinal fluid, because if we don't, you will die, or certainly lose consciousness and then ultimately die. So it's no surprise that the central chemoreceptors respond to very small changes in hydrogen ion or pH. As we learnt already, that will stimulate the respiratory centres. Therefore, it increases the activity going to your diaphragm and intercostals, which will increase your breathing or ventilation. Therefore, you're blowing off carbon dioxide, and therefore your balance is restored. Okay, so this is a constant monitoring. It's a constant cycle. Now, why am I saying cerebrospinal fluid, and why is it influenced by CO2? Well, in fact, as we learned, as we will learn, because I'm going to say it now, hydrogen ions, the brain, you might have come across this term in anatomy, or last year maybe, don't know. The brain is heavily protected. I mean, part of the reason we have cerebrospinal fluid is that it's fluid. The brain is fairly mushy. It floats in the fluid, and it protects it. Otherwise, every time you hurt, you rotated your head or nodded your head up and down, your brain would bounce against the skull and it would be damaged. The other thing the cerebrospinal fluid has is a very controlled amount of ions. And given that the brain is a host of nerve cells and nerves function by changes of sodium moving in and potassium moving out during an action potential, the fluid also maintains an appropriate ionic balance. Now, what's controlling all that also is that we've got, any fluid in the body ultimately comes from where? Any internal fluid ultimately comes from the bloodstream. It's coming from the capillaries. What we have in the brain is a very controlled mechanism surrounding those capillaries. Now again, this isn't integral, but it's kind of setting the scene, and it's called the blood-brain barrier. I don't know if you've heard of the BBB, the blood-brain barrier. It protects the fluid surrounding the brain to make it really constant, because the brain nerve cells don't like change. They want it to be constant. For that reason, hydrogen ions cannot cross the blood-brain barrier. So if you've got hydrogen ions in the body, they're not going to cross into the brain. However, CO2 freely crosses the blood-brain barrier. So when we say carbon dioxide is what we're responding to, it really is the pH, but the pH will only change in response to changes in CO2. Because peripheral hydrogen ions won't cross the blood-brain barrier. Peripheral CO2 will. So if you've got too much CO2 in your blood, it'll cross the blood-brain barrier. You'll have too much CO2 in your CSF. That will trigger this equation. You will breathe more in order to get rid of that CO2. Does that kind of make sense? Yeah. It becomes a bit more relevant again later. So they're the central chemoreceptors. They particularly respond to changes in CO2, which changes the pH of the cerebrospinal fluid. But they're not the only things that we're responsive to. So in order to look at that, we need to pause a moment and look at our respiratory centres again. I know I introduced it early on. Now let's have a thorough look at it. Well, as thorough as we can, really. Just not very thorough, just between you and me. I've taken this diagram from Silverthorne. Lo and behold, good diagram. Thank you, Ms. Dr. Silverthorne. It puts into context, here is the brain, lateral view, here is the brainstem. Enlarge it, sorry if you're not here in person. Here is the brain, here is the brainstem. An enlarged view of the brainstem. This is the pons, this is the medulla. In colour, we have our respiratory centres. Now, I'm not going to worry about the detail too much because we don't really still fully understand it. You kind of think that we know everything there is to know about physiology, certainly at these fairly basic levels, but the respiratory centres are something that we don't fully understand yet. So for that reason, there might be some variation between different textbooks. Don't get too worried about the variation. It is representative of our level of knowledge. What we do know is there are three main parts of or three main components of the respiratory centres. And they're indicated, the ones in the medulla indicated in purple in this diagram, called the DRG and the VRG, and their full name is listed on the left-hand side of this overhead. And in the pons, we have the PRG, the pontine respiratory group. Now, let's not get too worried about what they actually do. As I said, we don't fully know, but I'm just going to give you the current thinking. But I'm obviously not going to assess this level in the exam. I'm not going to ask you to know what physiologists don't know, but I'm just putting it into context. We believe that the dorsal respiratory group, well, we don't believe, we know. The dorsal respiratory group is the respiratory centres that have direct neural connection to the diaphragm via the phrenic nerve and to the external intercostals via the intercostal nerve. and it's indicated on this overhead. It has the direct connection, the outputs. So the DRG, critically important. That is the major respiratory centre. We don't know a lot about the ventral respiratory group. However, what we do know is that in fact part of it has a cluster of cells that tends to be the pacemaker. Remember I said the respiratory centres act like a pacemaker? You know, you have a basic set of action potentials making you breathe in, and then you have quiescence, no action potentials making you breathe out, resulting in you breathing out. We believe that the VRG has these pacemaker cells, and they control the DRG, which has the connections to the muscles. Nothing too complex there. The pontine respiratory groups, we don't really know much about that at all, other than that we think this smooths out our breathing. They tend to stimulate breathing to start and, more importantly, breathing to finish. So they tend to make sure you don't over-breathe. But again, hypothesis, not fact. Let's leave it no more complicated than that. The reason I show this then is because you can see in this diagram that there are other inputs other than carbon dioxide and pH that can influence these respiratory centres. Certainly the chemoreceptors are key, we spoke about those, but not the only thing that controls your breathing. There are higher brain centres which feed into the PRG, and there are sensory inputs from other parts of the body that feed into the DRG via cranial nerves 9 and 10. And if you're into anatomy, and this is testing me from my anatomy days, 9 and 10. 9 glossopharyngeal, 10 I know vagus. 99% sure that's correct. They're the sensory fibres that can also have some impact. So what are these things doing? Well, let's simplify it. This is a summary, and I think a pretty good summary, of all the things that can modify your breathing via the action of the respiratory centres we just saw. Let's go through it. Central chemoreceptors, we've already discussed that. They are the most important. They're responding to changes in CO2 and pH, which is one and the same thing, in the cerebrospinal fluid. Okay, already spoke in detail. They are important. They're not the only things. Believe it or not, we have connections, sensory connections, via the receptors in muscles and joints. Now, I don't want to go into too much detail, even though it is kind of interesting to each of those, but you probably never noticed, if you do athletics, if you did sort of sprinting athletics like I do or did particularly, you tended to breathe very quickly straight after you start your run. Now, you might say, oh, that's because my CO2 were built up. Well, in fact, we'll talk about that next week, that in fact you tend to increase your breathing before CO2 builds up. So it can't be in response to the CO2. And physiologists have often wondered how this happens. We think that it's these receptors in the muscles and joints. So as soon as you start working muscles, that stimulates, and here we see a positive sign, meaning stimulation, that exercise can stimulate the respiratory centres in isolation from changes in CO2 and pH. Okay, so that's what that means. Now, I say for the 9th time, this is nowhere near as important as the central chemoreceptors. Irritant receptors, again, just anomalies. Again, don't get hung up on these aren't critical, but they're involved. The irritant receptors in your airways can inhibit your breathing. Now, why might that be relevant? Well, if you've got some dust in your airways, what's the best way of removing dust from your airways? Cough. Now, obviously, cough is a massive expulsion of air. Now, there's no point trying to cough air out when you're still trying to breathe air in. Can't happen. So irritants inhibit the respiratory centres, allowing you to cough and by stopping you from normal breathing. Kind of makes sense. Stretch receptors, again, if you read, and obviously you won't, but if you read a textbook that's 20 years old, stretch receptors in the lung were considered to be really important to regulate breathing. Now we basically realise they have very little role, if any. Well, certainly some role, but it's a minor role. They inhibit your respiratory centres. Basically, it stops you over-breathing. You know, how do you know that you've finished your normal tidal volume of inspiration? Well, some people believe because the stretch receptors tell you that you've inflated your lungs enough, and that inhibits your respiratory centres. Okay, it certainly plays a role. Higher brain centres, particularly via the PRG, as we saw in the last one. Obviously, you can voluntarily change the way you breathe. Now, I can say, hold your breath. You probably wouldn't, because you'd say, why is he telling me to hold my breath? But if you did want to hold your breath, you can, to a degree. Now, notice, you can never hold, well, never. I don't think there's been any recordings I know of somebody holding their breath voluntarily to death. I remember we did this prac, and lo and behold, and I don't mean to disparage physio students, but it is kind of part of the story, that they did a breath-holding prac. And some of you who do the prac subject in physiology, PPB, will do this very same prac. It's one I devised a number of years ago. You hold your breath, and you tend to look at how you know, what controls you not being able to hold your breath indefinitely. And we had a competition, not a competition, sorry, we had, had to hold your breath until you felt uncomfortable. And lo and behold, there was this physio type who sat in the corner and held his breath for about 3, 4, 5 minutes, was starting to go blue, and sort of said, well, enough's enough, you don't need to do this. And he just wouldn't breathe. He just continued not breathing. So not that I had any pleasure in doing this, but you punch him really hard in the stomach, and that forced him to breathe again. So I wondered if he could at least hold his breath to losing consciousness, maybe, I don't know, it's obviously a specially highly motivated, in brackets, stupid person, but normally you can't do it. So, when you have kids, your little kid comes to you and say, give me $10, and you say, no, I'm going to hold my breath until I die. You can just say, go ahead, have fun. And you don't need to worry about the child protection welfare people coming to your door the next day. I won't be able to hold a breath till dying. Enough of that story. Pain is the other thing. Some people tend to hysterically hyperventilate due to emotional things or pain. Generally, you cut yourself, you're hurt, you tend to breathe more deeply. Why? Nobody knows. Probably of no consequence whatsoever. But obviously there's a connection between pain and other emotional stimuli and your respiratory centres. You do respond to certain emotions and pain by increasing your ventilation. There is no physiological need for it, but it is a connection. And finally, peripheral chemoreceptors. Let's talk about those. They are the second tier of regulation of our breathing. I'm leading in well today. Peripheral chemoreceptors, let's discuss them in more detail. As the term suggests, they are not located in the central nervous system. In fact, they're located in the aortic arch and carotid body, which are located in the carotid arteries. Now, two very quick things I need to say about that. Why would they be the aortic arch and carotid body? What's so special about the aorta and carotid arteries? Yeah, they're probably two of the most important arteries, or the most important arteries of the body, because the carotid supplies the brain with blood, and the aorta supplies the major abdominal organs with blood. So if you want to measure a chemical in the blood, and they said you can do it in two vessels, you're obviously going to say carotid and aorta. They're the two big vascular supply vessels. So perfectly understandable. Second thing I want to say, you might have heard of the aortic arch and the carotid arteries in terms of regulation of something else. No surprise, because they're critical. Who can tell me what the other nerve cells these parts of the arteries have? Semester 1, Year 1 option. Baroreceptors that regulate your blood pressure. Where are the baroreceptors located that measure your blood pressure? Aortic arch and carotid arteries, for the same reasons, the two most important arteries in the body. They're not the same thing, they're next to each other. So that's the familiarity that, with a prompt, you now understand. Okay, these chemoreceptors found here are sensitive to pH a little bit. Sensitive to partial pressure of carbon dioxide a little bit. And we'll see why in a minute. But really sensitive to partial pressures of oxygen. By really sensitive, sorry, comparatively more sensitive to PO2. Now you might say, why? Because remember, the central chemoreceptors are not sensitive to partial pressure of oxygen at all. They don't care what's happening to oxygen. Does that mean you and I don't care? Well, in certain circumstances, we need to care. So if the central chemoreceptors don't care, something does have to. It's the peripheral ones. So particularly in response to low levels of partial pressure of oxygen, reduced partial pressure of oxygen, you will stimulate the peripheral chemoreceptors, which feed to the respiratory centres, feed to the muscles, and increase your breathing, as we've learnt before. It's all about modifying your breathing. And obviously, if you increase your breathing, you're going to increase your PO2 back to normal. The big rider, as I've said 10, 20 times, we are much more sensitive to carbon dioxide than oxygen. We'll see in a minute why. Just before we do that, I just wanted to show you a diagram of the location of the peripheral chemoreceptors. Nice diagram, doesn't tell us much more than that. But here you can see the carotid bodies in the carotid arteries, just where the carotid artery bifurcates or divides into two, either side, because one runs either side of the neck. And the aortic arch, of which there's only one. The aortic arch is where the aorta arches over in order to go down to supply blood to the major visceral organs, abdominal and visceral organs. Now, they are nerve cells because, as you know, the best way to communicate rapidly between point A and point B in the body is via nerves. These are sensory nerves responding to partial pressure of oxygen changes, particularly. Now, let's look at how we respond to PO2. And here's a nice diagram from Widmeyer, but again, it's not too complex, so you've got the diagram on your lecture notes. X-axis is our PO2 of our arteries. Don't care what's happening in the veins. It's our arteries because that's supplying blood to the tissues. And on the Y-axis, we've got pulmonary or minute ventilation. Now, minute ventilation is the same as pulmonary ventilation. I'm sorry, there's two phrases. There just is. It's how much you breathe per minute. So let's look at this. At a PO2 of 100, which is normal, that's our set point. That's our homeostasis. Our pulmonary ventilation or minute ventilation is about 7 to 8 litres per minute. We've already learnt that number. Drop your PO2 in your body to 90. Does your breathing change? No, not much. Drop it to 80. Does your breathing change? Again, not much. Drop it to 70. Does it change? A little bit. Drop it to 60. Does it change? A little bit more. Drop it below 60 and you get a massive increase in your breathing. Why do we have that relationship? It's pretty straightforward if you think back to what we learnt yesterday. Bottom left-hand diagram of this overhead is what I showed yesterday. What did we learn? At a PO2 of 100, our hemoglobin is fully saturated. 90, still virtually fully saturated. 80, still fully saturated. 70, still virtually fully saturated. 60, starting to drop. Below 60, massive drops. So now you can see, why does our ventilation increase dramatically at low PO2s, less than 60? Because it's less than 60 where our hemoglobin saturation starts to drop dramatically. No coincidence, cause and effect. So that's why you and I, as I said earlier, are not that sensitive to changes in PO2. We don't need to be. It's only when our PO2 drops below 60 that we start to affect the oxygen supply to our tissues. So do you or I care that our PO2 is 90, 80, 70? Not at all. Our breathing is still normal. It's only when it drops below 60 that suddenly these chemoreceptors kick in. Now you might say, we'll talk about that in a minute. I've got a good story about that, surprise, surprise. Now, flowchart, not going to waste your time. Flowcharts, I like flowcharts, we established that. If you like flowcharts, your lucky day is today. If you don't like flowcharts, I'm not going to indulge, I'm not going to waste your time. This just comes from Widmeyer, I like it. It's summarising what we've discussed. Decreased PO2 that you breathe in, decreased alveolar PO2, decreased arterial PO2 because they're always in equilibrium. We've discussed that in previous lectures. If it's the PO2 drops below 60, stimulates your peripheral chemoreceptors, they'll send action potentials to your respiratory sensors, they'll send action potentials to your muscles, you will breathe more, your PO2 will go back to normal. Great. What about central chemoreceptors? Are we very sensitive? I told you before, yes, we're incredibly sensitive to CO2 and pH. Why? This tells us why. Really nice diagram in Widmeyer. Apologise it's not in Sherwood, but you've got the overhead here to look at. PO2s, our set point is about 40. So at a PO2 of 40, and Widmeyer has made a small error again, that dot is before 40, so if we move it up a little bit to 40, we see the dot should be here, doesn't matter. At a PO2 of 40, which is our set point, our breathing ventilation is about 7 litres per minute, which is normal, as we said. But if we change our PO2 from 40 to 44, look at the massive increase in ventilation that has, massive effect on ventilation that has. So any small change in PCO2 leads to an immediate and severe increase in your breathing. So we are obviously very sensitive to changes in PO2. Now, I've already told you the answer as to why. Why are we so sensitive to changes in PCO2? Because that will change your pH. Changes in pH kills your nerves. Killing your nerves kills you. That's why we're sensitive. Flowchart. Carbon dioxide, again, looks a bit more complex, but there's nothing new I haven't spoken to you about. Have a look at this flowchart if you need to. Increased PCO2 in your lungs increases PCO2 in your body, or it could be you're generating more CO2 because you're exercising, whatever. This will move to the blood-brain barrier because CO2 can cross the blood-brain barrier. This will increase your CSF, hydrogen ions, stimulates your central chemoreceptors, stimulates your nerves to your muscles, stimulates breathing, your pH and CO2 will go back to normal. Your peripheral chemoreceptors play a small role as well. They're a little bit sensitive to pH, and so they're activated a little bit, but they're not anywhere near as important as your central ones, as I've said time and time again. That's your flowchart, nothing new there. The reason we're so sensitive to CO2 changes, as I said, is because CO2 changes your pH due to that equation I showed earlier in this lecture. And this just enforces. What is our set point for pH? A nice neutral 7.4. At a pH of 7.4 or slightly over, our ventilation is normal. Any small, tiny change in your pH to become more acidic, so any drop in your pH, which is more acid, you get an immediate and linear response to your breathing. That's because this is not good for body function to have a more acidic pH in the nerves surrounding your brain. Okay, so that shows you how sensitive we are. Totally different from PO2. Flowchart, not going to waste your time, already did it. Oh, no, that's a new flowchart. Remember. Why do we, you might say, okay, I get all that, happy with all that, punchline, 10 minutes to go, what are you going to bore me with the last 5 minutes? Well, I've got one thing to say. Our peripheral chemoreceptors were also, remember they're principally responsive to PO2, but in our lecture notes we did say they're partially responsive also to pH. They respond to changes in pH. Not of the brain, because they're not in the brain. They don't know what's happening in the brain. But what's happening in the body. Now you might say, why do I have central chemoreceptors responding to changes in pH in the brain? Why do I need then peripheral chemoreceptors responding to pH in the blood? Well, remember, hydrogen ions, which is acid, cannot cross the blood-brain barrier. So can you think of any circumstances where the pH in your blood, your arterial system, will drop? Not related to CO2. Yeah, well done. So the question, I didn't ask that question very well and you still answered it well done, but I'll ask the question more clearly. We have learnt with the central chemoreceptors, increased CO2 crosses the blood-brain barrier, converts to hydrogen ions, changing your pH. You respond to it because it'll kill you if you don't. But if you've got a change to the pH in the body that's not related to CO2, because if it's related to CO2, the brain will know about it. If it's not related to CO2, that hydrogen ion will not cross the blood-brain barrier. You won't know about it. Okay, it's not going to kill your brain, but it might kill peripheral nerves and other organs. So you still need to know about those rare, relatively rare circumstances. When might that happen? Well, we had a good answer there. You're exercising. What's a byproduct of increased muscle metabolism? The production of lactic acid. Now that lactic acid can't get to the brain. You want to get rid of that lactic acid because you don't want it to influence your body function. Now, you will learn with Stuart in a couple of weeks' time the kidney will have a big role in that, long term. But your ventilation can act short term. Another reason, you may, lovely discussion to have after lunch, you may have diarrhoea. You will be excreting large amounts of bicarb. Now, if you drop bicarb, you are also influencing, you're getting a build-up of hydrogen ions, because if you drop bicarb and not hydrogen ions, there's an imbalance. So having diarrhoea will also affect your body's pH, and vomiting in the other direction. So there are metabolic conditions that can affect pH. So we need to be able to respond to those. What do we do? Again, increased acid or decreased pH in the arterial system that's not caused by CO2 can still be resolved because our peripheral chemoreceptors will detect it. They will increase your breathing. You will blow off CO2 and your pH might start to approach normal again. It's a short-term fix. The kidney is a long-term fix, but we need to have that. Is that clear as to why we have that nuance? And this, mother of all, flowcharts brings everything we said together. What happens if you drop your PO2? What happens if you've got a drop in pH that's caused by something other than carbon dioxide? And most importantly, what happens if your CO2 partial pressures increase? Through either the central or peripheral or both chemoreceptors, you will increase your breathing, thus rectifying all those conditions. And that's how you and I